Water is still flowing in. Yeah, it should be okay. Okay, so first a little erratum of the referring to the first part. So the VXX is not an ETF. It's not a double leverage one. So let me put it a bit higher up here. Is it better? Or I don't know. Yeah, so it is actually just a synthetic 1 month constant maturity futures contract. So it means, okay, when you buy a future contract, obviously it has a finite maturity. So you have to do something when you get close to its maturity. And so this VXX does the work for you by constantly maintaining 30-day, or yeah, basically a 1 month maturity for the futures contract by taking an average of the next 2 contracts. Typically, if you have 20 trading days in a month, then you will roll each day 20th of it, so 5% of the contract. So you will buy 5% of the second contract and sell 5% of the first one. And it's an interesting product which has a tendency to go down, 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 and down for multiplicity of reasons that we can address separately. So now I'm going to talk about different facts on volatility derivatives. So first I will just review different products. Essentially some are based on historical volatility, other ones on implied volatilities, and showing some arbitrage links and models that have been used, and something for especially focused on the options on realized variance before concluding. So let's start. Products linked to the historical volatility. So definition of historical variance or realized variance, it's this one here. And you have obviously the variance swaps, but the volatility swaps are quite popular. So the variance swaps can be virtually replicated perfectly. Actually, you have many sources of frictions and imperfections, but the volatility swap will give you a payoff that depends on it's the square root of something tradable. So itself is affected by the notion of volatility, which means it becomes model dependent. So you have corridor variance swaps, so where you will accrue this quantity only when you are within two levels, and you have options on those quantities, and you have in terms of listed products, actually those I think are defunct now. Implied volatility product, so you have obviously the VIX, the old VIX. This was before 2004. It was computed, actually it was based on the S&P 100 as opposed to 500 now, and it was just a sort of average of the closest to the money implied volatilities, as opposed to the new VIX, I mean the new of the 2004, which is incorporating all the strikes to have something which is more representative of the global level of volatility, and that authorizes a perfect replication. By the way, if you're interested in the historical notes, there are 2 classical references for the origin of this of those contracts of variance swaps and VIX, based both on the use of this 1/k² weighting on all the strikes. So one, it's Anthony Neuberger. He had a paper called the logarithmic contract. I think he said if we had logarithmic contract, we could actually convert it into realized variance through the delta hedging. And the other reference, it was actually my paper, Arbitrage Pricing with Stochastic Volatility, back in 92, was a published version in Risk Magazine in 93, which was actually independently saying, yeah, you can combine options that exist to create this log profile, to delta hedge it, to extract the realized variance, and you can actually do it on a forward period. You can virtually define and lock-in synthesize the notion of instantaneous forward variance. And so it was a nice step compared to the classical stochastic volatility models that were always saying, yeah, but we cannot trade volatility, so we need to define arbitrarily some risk premium for this process. So what I showed is that actually if you have options that are existing, you can combine them in such a way you can extract, you can purify them to get the variance. So basically those two approaches, Neuberger and mine, have been the ancestors of both the variance swap and the VIX. So we have swaps and options on the implied volatility and in terms of a listed product. So we have the VIX futures, and now indeed it's not written here, but you have plenty of a very rich market, as I mentioned, of options on the VIX. And Volax was the first European contract. It was on the DAX, and now we have VSTOXX with plenty of options. Yeah, so let's carry on. VIX futures pricing. So here, generic comment that I already alluded to on volatility trading. So it is that a simple option, so a call option here, it's actually a very complex product because the sensitivity to the spot, which is to the price, which is the delta itself changes with the spot price from 0 to 1, basically. And the sensitivity to volatility, which is a vega, here is centered around the strike. So it means that it's a simple option, but it bundles in a very complex way exposure to both price and volatility. If you want to do volatility trading, you have to eliminate this conditioning of volatility to a specific strike. So a way to do it will be to add up plenty of strikes, and ideally it would be by reconstituting a log profile, because you can show it has constant gamma vega. So, sorry. And here, if you use different strikes, so it means you will have this kind of Gaussians here, and if you add them up, you create a profile of constant, actually, constant vega. So in practice, okay, maybe I don't go through all the details, but the VIX formula, so this is to compute what's called the spot VIX. So it's an index. Again, it's not the thing you're trading. You will trade guesses of the future values of it. But at every point in time, I think it's more or less computed every 10 seconds or something like that. You have the VIX is computed. So here it's VIX squared. So it's the square root of all the thing here, which is based on the price of options. X, it means out of the money options. So it's calls for high strikes and puts for low strikes, plus a correction term due to the fact that usually the forward doesn't fall on one strike. And it's an approximation of the log profile. So, okay, let's go back to the mechanics of it. Log profile, so here, for instance, in Black-Scholes, it will have this value, but we have the decompositions, which is quite well known. Some people call it the Carr-Maiden decomposition. When you have a function of S, you can always decompose it as a constant. So if you decompose around the value, let's say S0, so it will be a central value. Okay, it's a bit like a Taylor expansion, where you would have different orders. You have the value plus a linear term plus a higher order terms. You can do the same thing to have a constant value plus a linear term, but instead of having other polynomials, you have a portfolio of calls and puts. Sorry, yeah, which is what we have here. So in general, if you have a function f of s, you can write it as a continuum of calls and puts, with the coefficients being the second derivative of the initial function. This is why the 1 over k squared is appearing by differentiating twice the log. So it means the corresponding portfolio is this one here, with in the case of a continuum of strikes. On the market, you just have finite numbers. So this led to this VIX formula. So in practice, I'm sorry, probably you don't see much, but what you do, this was a very old slide actually, but you look at, here you have the calls and here you have the puts. You have different strikes, and you have the bid and an ask price of the option. So what you do first, you compute the mid for each strike, and then you identify the strike such that the mid of the call is closest to the mid of the put. You know, for a strike which is the forward, you should have equality by conversion of the call price and the put price. So here we induce a candidate for the forward through this rule of equating as well as possible those mid prices. And so here you got 1090 as this one. And so it means you use the strikes higher than this proxy of the forward for the calls and lower than that strike for the puts. Also you have exotic rules about which strikes are part of this summation. And as I mentioned earlier, it depends on the liquidity of them. And so, for instance, if you have 2 strikes in a row which are not, which do not have a bid, I think, then the summation is truncated there, even if there is another one further. So it means it's not reaching the whole of the log, but just part of it. So if what was quoted was not the VIX, but VIX squared, which is essentially this log, so we would have, in a frictionless world, and let's say no carry terms, let's say no interest rates, to make it simple, a perfect replication. In the sense that at time T1, the spot VIX would be the price of the log profile maturity T2 at that time. And what we have to price for if we had a futures contract on it, so essentially it would be the price today of a portfolio which will be essentially a log at T2 minus a log at T1. You have negative coefficients minus 2 over delta T there. But in short, you could replicate it by buying the options maturity T2, selling the options maturity T1, and always with the weighting scheme of 1 over k squared. So the idea is that this would capture this notion of forward variance. In practice, unfortunately, it's not the case. The VIX contract is based on the square root of this quantity. So the logic will be the classical approach would be to say, let's consider this quantity as traded as a new underlying, and we have to price actually the square root of it, which is a nonlinear payoff of something that is traded. And so it requires some notion of volatility of this underlying, which means vol of VIX, to do it properly. This is a classical approach. So here, the portfolio I mentioned, which would replicate the VIX squared by buying the T2 options, selling the T1 options. So we look at its value it will have at time T1. We know the value of it today at time T0 because we knew at T0 the T2 options and the T1 options. And actually, the VIX will be the square root of this portfolio. You have a convexity, a concavity bias here, a Jensen bias, due to the fact that you have an uncertainty around this PF of T1 value. So the naive approach, which would have been to take in a deterministic world this value for the VIX, actually it is a proper upper bound, but it's not correct because you have to take into account the volatility of volatility, and there are different attempts to try to compute this concavity here. This actually is not the best approach, because if you want to have a trading interpretation of this, it would mean that we consider at every point in time this portfolio is tradable in a liquid fashion. So it means linear or affine profile here are available. And so we would try to follow this intrinsic value by adjusting, by delta hedging it with something locally linear. This is not a proper thing to do, because if you have two related quantities, basically in this case the VIX and VIX squared, which is a portfolio, so VIX and a portfolio, what you should do is to look at the most liquid one and to use it as a trading, hedging instrument. So instead of trying to use the illiquid portfolio and to trade it dynamically to replicate this, you should rather do the other way around. You should actually use, and this is something that works once that the contract exists, which is the case, obviously. So you should use the VIX futures to dynamically replicate the portfolio, which will have a value equal to the VIX squared at the end. So when you do it, you obtain actually an estimate which is much more verifiable, much more tradable, much more implementable than the other one. Basically, it means just, in this case, selling initially this portfolio of the T1, T2 options, and having a dynamic hedge of it with the VIX future, which has a small bid offer, and it's quite liquid. Well, okay, so bias estimation, this was an old thing. It's what we had at Bloomberg for the estimated values. Here it's an example of what you need to have behind the scene in terms of different tools to manipulate all this, to be able to compute the forward variances on different periods. Okay, so it was a few technicalities, but the typical problems we have with the VIX is the need to use all the strikes to replicate really the log profile, and you just have a few that are available. The other one is the fact that what is quoted, it's sigma, and what you can lock in is sigma square. So you have this convexity bias between those two notions, which create problem. So now it's the slide that you had seen before. Here it's a simplified version of it. Well, it's another one, but I think I have to skip it here. And we go to volatility modeling. So it's the references I had mentioned, so Neuberger. Those are the dates of the working papers, actually the published one. So it was not addressing the same problem. Mine was 93 and Neuberger 94. But yeah, I think I have, I'm sorry, I have too much material. I have to go quite quickly through this. Well, an approach used by many people to price volatility derivatives, indeed, it is to calibrate a kind of classical model on for the stock price, like Heston or different variants of it, and then to use the calibrated volatility process to price the volatility derivatives. Actually, we have serious problems with, for instance, Heston. When you calibrate Heston to the market, you tend to find a volatility of volatility, which is something like 2 or 3 or more times too high compared to what you observe in practice. What does it mean? This is an implied vol-vol. Vol-vol is volatility of volatility. And you can compare it with a historical vol-vol, which means historical volatility of the implied volatility. Typically, you look at how the implied volatility surface moves through time. And the problem is that here, this number we find by fitting the parameters to a snapshot of the market now. It tends to be too high. Why is it so? It's because in Heston, the only mechanism you have to generate a skew, it is through this correlation between the Brownian of the spot price and the correlation of, the Brownian of the volatility. So essentially, the slope depends on the vol-vol times the correlation. Correlation indeed is between -1 and +1. So if you want to have a big skew, you need to have a big vol-vol and far too high. Because here you don't have a mechanism like, for instance, local vol to absorb a part of the skew. You try to explain it only through one wrong reason. That's why in the market it's very popular to have SLV, stochastic local volatility models, which are a kind of mix of stochastic vol and local vol. They have a component of local vol to absorb, to avoid this kind of behavior. So here is the instantaneous variance of the price, the small v here. Yeah. No, I mean, what is relevant is alpha times square root of v. Yeah? And actually, one of the consequences of having too high alpha, it is that it tends to violate the failure condition that determines whether you reach zero or not. And so that's why if you generate Monte Carlo by Monte Carlo path of this, which is not so easy because it's, a naive Euler scheme would generate negative values. If you truncate, you add up some vol-vols. So you have to be a bit careful for this. But when you generate paths of this, often you get a volatility that reaches zero and bounces there. To try to understand how it works, actually, okay, imagine an Einstein-Uhlenbeck process, let's say mean reverting to zero to make it simple. So it goes, it will cross zero a lot, and the square of this Einstein-Uhlenbeck process will be a CIR process, so something like this. And obviously the square of it, if the initial process was crossing zero a lot, so obviously it's something that will bounce to, well, it has the same zeros. So it gives you an idea of how this thing tend to behave in general. So you have to be careful about the calibration of those models in general. Yeah, as well. So it's another disconnect with the historical behavior. But as a rule, it's very important to make sure that your model calibrated to the current price of the options is generating something which is not absurd. It should be also in line with the historical behavior. I mean, otherwise you will have very, very different, very bad hedges. For instance, with the big alpha here, it means that you will expect, for instance, that an option which has a big Volga, a big sensitivity to the big convexity to volatility, you will, the model will think that the option will capture a lot of value from this convexity because the volatility is supposed to move a lot. And so it means this will correspond to a high theta, and if you trade the option, you will see you pay a high theta that is supposed to be compensated by these big moves in volatility that actually do not happen. So now I must say this is a work I've done mostly in 2004, 2005. I must say I had done quite a few things in the 90s about volatility, and obviously it would be very pretentious to think that you're not expecting any surprise anymore. But those results maybe have been amongst the biggest surprises I had after the year 2000. And yeah, basically there were some concepts that I'd not realized could be important. So if you have on the market a strong skew, yeah, so it's a bit, it's kind of linked to actually to the Heston comment, but it means that necessarily the volatility itself will have to move quite a lot, not necessarily in an independent way like in the Heston, but it will actually be linked to the spot level. And basically, okay, let me try to phrase it differently. If you have a strong negative skew, typically it means that volatility is supposed to be high when the spot price goes down. And you have a high correlation between the price and the volatility. And the question is to know how to transfer this correlation between price and volatility and into a link between option on price and option on volatility, which is not direct, but it's possible to do in some to some extent. So let's try to see what we can do. First, at the time, there was an approach by Peter Carr and Roger Lee with strong assumptions. Mostly it was uncorrelated increment of spot and vol. A technical term for this would be an Ocon martingale. So it's essentially a process that would generate at each point in time a symmetric skew. So under this assumption, so everything here is a simplified version, and I think it's in the Bachelier terms as opposed to Black-Scholes terms, so it means normal convention as opposed to log normal. But yeah, the point is the following one. You can use the price of options because here x is the underlying. So here it's a certain function of x, and you can replicate it by a portfolio of options. So you can show that with this independence behavior. So if you suppose that you have a random variance like this, capital V being the realized variance, so actually you can compute this as that and link actually the moments of the stock price and the moment of the variance. And so after, if you manage to invert this relationship, you will be able, hypothetically, to read from the skew you had on the underlying to compute the distribution of the variance. But I mean, let's say it's interesting, but really we cannot justify the assumption of independence. It's not the way the market works. So here, my kind of little revelation at the time was essentially this one. The classical, so if you have a call on realized variance, so it means that, okay, realized variance is the square of the historical volatility. So it's indeed something you observe ex post as opposed to the implied variance, which is ex ante. So you need at the end of the period to know that. So the payoff of the call variance, so you observe the realized variance and you receive what is in excess of the strike. Realized variance is the payoff of a variance swap. A variance swap is just receiving realized variance and paying fixed. So the logic, in general, if you have an option on an underlying, here the output, the payoff of the variance swap, so let's call it, I don't know, I've already X, let's call it Y, the underlying. You would be tempted to say, okay, to price an option on Y, I need to know the volatility of Y, and I will use Y as a hedge, so I will have a dynamic hedging of Y. In that case, it would mean dynamic hedging as a variance call with variance swaps. And variance swaps are making use of all the strikes. It's always buying and selling all the strikes together with this 1/k² coefficient. And I was wondering whether this was the best thing to do, knowing that through the strong correlation between volatility and price, maybe you could do something better by using in a more selective way some strikes and not other ones. So let us see what we can do. First, to understand that there is some hope. If you look at a limiting case, I have to assume also that there will be no jumps, but the limiting case of the VIX not being 30-day index, but actually kind of instantaneous volatility index, then you can use a couple of properties here to get the following result. If you have a convex function, so V would be the instantaneous variance. So by a nesting property, you have the conditional expectations. You can condition by a value of the underlying. And now, due to the convexity of F, so you can use the Jensen's inequality here. And due to the property I showed in the paper, Unified Theory of Volatility in '96, but it's also called the Gyeonggi property. Yeah, it's the expectation of the instantaneous variance conditioned on the value of spot price in the future is the local variance. So you eventually get this property. If you do it with square root, which is concave, it's the other way around, but you would get that expected, so the VIX would degenerate to the instantaneous volatility, and in that case, you would have expectation of the instantaneous volatility is lesser than the expectation of the local volatility. And you can show that you can enforce this relationship by using specifically some strikes. Actually, I gave a talk at the last Bachelier conference in New York about it. So now let's try to understand an important concept. It is that if x of t, so at a given maturity, see if the spot price is not normally distributed. Again, I reason in Bachelier terms instead of Black-Scholes to simplify the presentation. But if basically the skew is not flat, it means that the realized variance cannot be constant. And it's linked actually to the Dambis-Dubin-Schwartz result that continuous martingale can be seen as a continuous time. A time change Brownian motion, and actually the time change will be the realized variance, the quadratic variation of the martingale. So let's try to go through the reasoning here. So if you have a continuous local martingale, if the quadratic variation at a certain maturity is a constant, so it implies actually that x of t is Gaussian through this Dambis-Dubin-Schwartz argument, for instance. And so it means that if it's not Gaussian, it is not constant. And if it's not constant, it means you can say something about the value of options on it, hopefully to find some lower bound. Let's look at it in a more of a trader's logic here. So if you have an option, let's say, on the underlying, and you if you sell it and you delta hedge this option, what is your risk? Obviously, it is that the realized historical volatility will be higher than the implied volatility. You sold that. So what is your risk is that you have a high historical volatility. So a possible hedge against that, it is to buy a call on the realized historical volatility or realized variance. So here we start seeing the different ingredients taking shape, how they can be combined to try to improve or to get dominance results and that are linking the price of options that we sell and actually the variance calls here. So to do it, to manage to have a tight link actually between the excess variance and the hedge of the other one, you needed to do something which is a business time delta hedge as opposed to a calendar one. So I'm going to explain what it means. So as I said, we work with a Bachelier convention, not the Black-Scholes. It's more symmetric, it's nicer. And if I have a certain function f of x, I extend it to, so basically it will be a final payoff, and I extend it to a function of two variables where I have a variance parameter. So basically, it's the value of the payoff f when you're at x and still with a quantity of variance v to come. So in other words, f of v will be the convolution of, it's an expectation of the final payoff, so knowing that you're at x and you have variance v, you convolve with a Gaussian of variance v, as shown here. So obviously, for zero variance, you're back to the final payoff. And it satisfies a kind of heat equation here. So it's the reverse convention of the Bachelier PDE, because V, the variance, is a remaining variance. It will decrease as you go through time as opposed to small t advancing in time. So it satisfies this. So the classical calendar time delta hedge that you all know, so it means if you hedge with a certain volatility sigma, so when you apply Ito to this function here, you find that you have the delta hedge here. You have what you gain through the theta, what you lose, you lose through the theta, what you gain through the gamma. And so you can, due to the kind of heat equation, you can write it like this. So basically, this will be the mishedge. So it means you have the delta hedge here, and you will, it's not self-financing. You will make money or lose money according to whether the realized volatility here will be bigger or smaller than the anticipated one there. So this is over a dt time interval. If you do it along the whole path, you have to integrate. And what you see is that you manage to replicate until time small t. Yeah. I mean, you have to add up those different non-self-financing elements here. So what does it mean? It means that the replication of the claim here will be highly path dependent, because it will depend on whether you encounter a big gamma or not, and it depends on how the realized variance, the instantaneous variance, is distributed when it's above or below the anticipated one. So it means the result will not be very tightly linked to the final realized variance, because it will depend on how it was aligned with the gamma or not. Something that we will use, which is interesting, is if you do it with zero volatility here, so it means that you just have to pay the Ito cost to always replicate. You always follow the intrinsic value, but you have to pay for the curvature that you miss through those terms here. So this is just a review of the classical delta hedge, which is that when the volatility does not behave as expected, so it's not constant, you have a tracking error term, which is like this, and which is highly path dependent. Now, if you do the business time delta hedge, to make it clear, here the parameter of remaining variance we had, it was this familiar term that you see in Black-Scholes or in Bachelier. So it means it decreases linearly through time, or in other words, we have a constant implied volatility. Now here, what we're going to do is actually to use kind of strangely an remaining variance that depends on the realized variance so far. So actually, there is an interesting metaphor here to understand what's going on. you could see the act of replicating an option as a sort of having an initial reserve of energy that you're going to spend through the replication process according to the realized variance. You can see the initial variance parameter you have as a quantity of gasoline you put in your tank, and you're going to spend it a long time. And the question is to know whether you will you will reach your maturity cap T. Are you going to run out of gas before or not? Here it tells you that you managed to replicate your option until you ran out of gas. So it means when the realized variance here reaches the initial variance budget that you had here. So here you see that the variance parameter that you're using depends on T in that way. When you apply Ito here, you have the classical term here. So as usual, you will have second order term with respect to X, which is stochastic. This is not stochastic, decreases, it has finite variation. So you just have a first order term and not a second one. And when you use this heat equation, you see that actually those two terms just cancel here because you have dQV, dQV here. So it means that just a standard delta hedge here will perfectly carry on the replication. So there is no tracking error, but now the uncertainty is about for how long you manage to do it, which will not necessarily be the maturity. It can be before or after. For instance, here, if your realized variance is smaller than the initial budget, you will manage to do it until the end. I mean, sorry, as long as you have not consumed everything, you manage to replicate exactly this quantity from the initial price plus your delta hedge here. So you manage to replicate exactly your payoff until the time tau where your realized variance reaches the budget. Basically, you run out of gas. You've consumed everything. Okay, so I don't know whether it will be very explicit here, but if you start with an assumption of a 30% volatility, so here you would have the break-even points like that. And yeah, I have to reconstitute this. If for instance, if now you revalue with 29%, so you would have, if this is the remaining volatility, I don't remember the details, but essentially according to the value you use for the remaining variance, it will generate different break-even points. And actually, you will do the reverse. According to the realized move, you will see what remaining variance you should put in your equation to fall on the break-even points. One way to look at it, it's a bit like a trader with sort of basically lying to his management. So he knows that the manager likes to see zero change of P&L, something very, very smooth. And so every day, according to the realized return, he will readjust the revaluation parameter in his Bachelier equation to say, oh, look, boss, it's exactly, we're exactly on track. And so if it goes bad for the trader, for instance, he has sold an option that it moves too much, then he will have to tell the manager, we're still good, don't worry, I'm sure that there will be very little volatility until the end. And if it carries on being very volatile, so it means he runs out of gas, then he will explode and he cannot lie anymore, essentially. But so that's the interplay between the realized move of the day and the remaining volatility that you could put that generates actually break-even points that correspond to the realized return. Basically, once you do this volatility adjustment, it removes the second order term that you have in the delta hedge. Delta hedge removes the first order term. The business time delta hedge removes the second one. And your P&L actually just looks like the red thing. It's a third, dominated by a third order term. So here I have an interesting illustration here. So I think that what we do here, we do everything in Bachelier conventions, but we generate paths under Black-Scholes. So it means that if the price goes high, then the realized variance will be high in absolute terms. It will be low if the price goes down. And here, what we do is we assume that we know beforehand what is the realized variance. And basically, if we make use of this knowledge in the business time hedge, actually, we manage to eliminate all the noise. So in other words, to simplify, so it means that it separates two issues. One is to have a guess, a proper or not guess of the realized variance, and the second one is the tracking error of the option. So here, obviously, there is no way to know in advance what the realized variance will be, but here it tells you that if ever you were right on your guess, then you will have you will eliminate the tracking error. So let's see. That's strange. Why a box? So let's go through a couple of slides. That's really the strategy. I'm sorry because it's not very simple, the whole thing. But so you sell a pair of F, and so L is a kind of a variance budget that you have. So it means you receive a payoff with a certain implied volatility that can be interpreted by this here, and you start delta hedging in business time. So if the realized variance is lesser than this initial variance budget, you're fine. So it means you have not consumed all your gasoline. So you arrive at your destination and still some gas in the tank. And so actually, this is a remaining gas, if you want, gasoline that you have. And you have some extra time value if F is convex. So you've managed to replicate the final one here. The problem is the following one. If the realized variance is greater than the variance budget, then it means you do run out of gas before. And so you don't manage to replicate until the end. Now the question is to know what to do. So you need to put more gasoline, but how much? If you put a certain arbitrary amount, actually maybe it will not be enough, maybe it will be too much. Actually, what you're going to do, you will add up the gasoline drop by drop until you reach the destination here. When you do this, you will pay the Ito term due to the convexity of the payoff. And it will correspond to actually to this term here. This is the cost of carrying on the replication between the time you run out of gas and the maturity, the Ito term here. And so this Ito term, if I have, I don't know whether I said it, maybe not, but so if you take a payoff with a bounded second derivative, I call it MF, the upper bound. So this, so I take, I say that this is lesser than MF, and I pull MF out of it. So I get this, and here it's the integral of the quadratic variation between tau and t, which is the quadratic variation at t, which is called v, and the one at tau, which was L. L, because tau was the time when you reach L, when you run out of gas. So you have this, and what do you recognize here? You recognize actually the payoff of a call option on the realized variance. I'm sorry, it's quite a few different steps here, but it allows you to say that actually a super hedge of the F payoff is this initial premium plus M over 2 call on the realized variance. Basically, if you're long this, then you can sell F and delta hedge. Either the variance, realized variance is small, it means you manage to, so this will end out of the money, but you did not need it because you've managed to replicate until the end because you still had gas in your tank. And if you run out of gas before, then this kicks in and does more than finance what you need to carry on the replication between the time you run out of that gas and the end. Yeah. Yeah. No, here, that's why I mentioned at some stage, we do it for a bounded second derivative, and we call it MF here, and we'll see that we can use it. This is the best way to use the property. So it's true, you cannot do it with just a single option. It assumes that you have some smoothness. But the goal here is not to super replicate a call option. It is to use these principles to actually obtain a lower bound on the variance call. So just summary of this slide here, it shows that you have a super replication of the payoff F by this initial premium and those variance calls. So this means that actually, seen from this, it means that this guy cannot be too cheap, otherwise it would be an arbitrage. This F here, it has a market price, implied volatility from the market, which will be a certain LF. And so if you have a L which is, for instance, smaller than LF, and you run all the thing, so here L determines the strike of the call. For all L, actually, by arbitrage, as this dominates F, you need to have the price of this being at least bigger, at least higher than, at least as big as that. So which means that basically the call cannot be too cheap, which is expressed here. Actually, you can show that for all F, we need to have this relationship. And now we are going to look for the F that maximizes this right-hand side here. So F was a payoff with second derivative lesser than 2. So as usual, we can write it as a combination of different options here. And we know that this has to be lesser than 2. And so we address the question, when is it that it maximizes this? And so essentially, you will have this weighting scheme here being 0 or 2, according to whether the implied volatility of this option here will be above or below L. Sorry, again, it's many different steps. It's difficult to absorb all this at a time. But so what you have to do eventually, it is to pick all the strikes where the implied volatility is above L, and you don't take the other ones. But you try to maximize this quantity here, and so you can write it as an integral strike by strike. And so basically here you see that when this is positive, you're going to have a coefficient 2. When it's negative, you put a coefficient 0, which means that you keep only the strikes where the implied vol is above L. So, yeah, exactly. It's maximized when the second derivative is equal to 2 for the strikes such that the implied vol is greater than L, 0 otherwise. now when we look at market values, so actually, if you had used just the standard argument of replicating, finding a lower bound just from the variance swap, if you remember, so the classical argument is to say, oh, if it's an option on an underlying realized variance, so we should first look at what we can do with a hedge with the underlying itself, which is the variance swap. In that case, for the lower bound, we would just get the intrinsic. Here, sorry, we get yes, I think, I don't see the color code here, but red is the lower bound that we get. And here it's different models calibrated to the market data. So indeed, we know that they will have to give a higher price. And for instance, Eston-based or SLV model with high vol was giving something substantially higher, but with a low vol something very close to it. So here it means that this lower bound is quite practical in the sense that it is very close to what we get with some calibrated model. If you want to go to the bottom of the lower bound story, actually, this was a kind of trader version because I summarize it here, and after I will talk about the full story. But the strategy is if you find on the market, the question is the following one: if you find on the market a variance call which is below this bond, how can you monetize it? So again, that's always the art of the arbitrage. It is to transform a kind of mathematical relationship which is true in average into something which is valid pathwise. And the way to do it is the following one. If you find a cheap one below the lower bound, you buy it, you sell all the options with the implied volatility is greater than this, and between the today and the maturity of the option, you delta hedge those options in business time, and so it means the delta is computed with a volatility parameter that depends on how much variance has been realized so far. And again, if you run out of gas before maturity, you carry on the hedge with a zero vol, so which is because the variance call will pay for this Ito term. If it's theta is greater than t, then it means you have managed to perform the hedge. So as usual here, if you find such a situation, so it means that you make a sure money to start with due to the difference between the market price of the variance call and the lower bound, and possibly more at the end. No, okay, here the conclusion is slightly repetitive. So my conclusion will be more what I mentioned with to go to the bottom of it, the real sharpest of the strategies. It's linked to this score embedding problem. And actually, so I've been working on it at the same time. I unearthed some papers of back to 76 on Root by Root and Rost, which are basically showing that in all the solutions of the score embedding problem, again, how to stop a Brownian motion in such a way it has a desired target density. And as I said, in trading terms, it corresponds to models calibrated to one maturity. So the one that minimizes actually convex function of that stopping time, it's called the root solution of the score embedding problem. The stopping time of the score embedding problem is the quadratic variation or the realized variance here, and we are talking about convex payoff, a call of it. So I had established that link, and the root solution corresponds to stop the Brownian motion when it just reaches some obstacle in the time price space. So many years of work have been done on this, but It's just for the people who are interested in this topic. By the way, I recommend a very good monograph by Jan Obloj of 12 years ago, I think, about the different solutions of the score embedding problem. Really, you read it like a thriller. I mean, if you're interested in the things, there are something like 22 distinct solutions, and it goes through the history of all of them, and it's very elegant. So I recommend this. Okay, so to conclude this volatility derivative stuff, so here I just wanted to show that actually beyond the classical link that we know between historical volatility, implied volatility, there are sort of more hidden principles that is very interesting to try to unearth, and notably the fact that if you have a strong skew on the market, it's due to the fact that volatility will have a markedly different behavior according to the spot price goes down or goes up, but for sure it will not have a constant value. It will vary a lot, and there are techniques shown here to show that, that it is possible actually to extract this variability to establish lower bounds on products like variance calls. So I will stop here. Thank you.